So now we're at the point of topic 1 where we can define what a function is. So here I've given two sets and I'll define a function on them, and then that will lead us to the definition of a function more generally. The first set is x here. That's the set of all you discrete math students. And the set y there is all the possible marks that you might get from following this course. Now I hope that that will of course be 85 or more. HG for the win. Please do get that. I do hope that you get a great mark for this course. Now we can define a function on these sets, or rather a function from that set to this set here. And we can write that. Let's call the function f for function. And we can indicate that we're taking elements from this set and assigning them elements from that set, function values in other words. So elements of x go towards elements in y, and that's how we write it up. And here x is the domain. Domain means home, so this is like our home where we start out. And this is our codomain, sort of like our home away from home. It's not quite home, but it's codomain. There we go. But it's a nice and warm and fuzzy place, especially if you do get for 85 or more in your mark. And that's what we also have to signify. That's where the function values come from and where they sort of end up, if you want. So the function itself is just defined by, in this particular case, by f of x, where x is a student, any of the students here, as the mark of x, or x's mark, if we want to be brief, want to describe it briefly. And you could draw it in terms of arrow diagrams that we saw before in connection with the Cartesian product of two sets. And so we have x there, a whole lot of students who are going to get some mark. So you have marks here, and you're sending them over to 100, yay! And this is the set of marks in total. So you got 99 here, yay, that's pretty good too. And then you have down to 85, yep, that's not too bad. And then you have the marks that I hope you don't get, from 84 down to 0. So let's see that all of you are getting a mark here. And this is a terrible pen. Let's find a better pen. Here is hopefully a better pen. Oh, nice pen, yay, cool. And 85, and lots of people are getting 100, yay, awesome, and we're very happy. Okay, so this was the set y, and we can say f goes from the one set to the other. Now, if you look at that diagram, that represents a subset of the total Cartesian product x, y. So if we write that up, function f going from y satisfies that we've got the ordered pairs x and f of x, where x is any element, so any student, for instance, satisfies that this particular set of ordered tuples or ordered pairs is a subset of the Cartesian product. So this is sort of a way of defining the functions. But we also have to have that some conditions are upheld. So we could write that so that for each, in this case, student, or more generally, each x in x, we have two things that are satisfied. Or you could write them as one, but the two things that are satisfied. Now, what could that be? Well, think about it. This mark-giving function, if you end the course and you want to get a mark, well, you would like to get a mark. You would like there to be a mark function for you. So that's the first condition. For every one of you, or more generally, every element of x, f of x exists. But furthermore, it's unique. So there's only one mark given. Like if you end the course and you've been to the final exam and you're given your final mark, except then you're given 3 final marks. You sort of wonder what's going on. Of course, you choose the highest, but that might be okay. But you could also be a little bit worried that something didn't quite work in the system and something broke down, and that wouldn't be great. So what you want is a function. So functions only have one function value. So not only does your function value exist, but it's unique. So f of x is unique. There are no more than one function value. So this is these criteria here. You've got these functions, or these objects that define these ordered tuples as subsets of the Cartesian product, so that these 2 conditions are satisfied. Well, if that is the case, then we have a function. So that's a way of describing or even defining what a function is. So now we can talk about functions, but let's first have some examples of what functions could look like and what they can't look like. So here we have an exercise. So you might want to pause the video and complete it yourself if you can. The objective of the exercise is to look at these 2 sets, x and y, and see whether these 3, f, g and h, they are functions on x to y. Now, if we recall what a function was, it's a function, or it's a thing that sends elements in x to y, so a, b and c to y, namely by giving each of these elements a function value. It could be any of the values there, but in such a way that there is a function value for each of these a, b and c in this particular case, and that it's unique. So you don't, if it were the mark-giving function from before, you get exactly 1 mark. There is a mark, so there is this function value for each of you students, and you also just want 1 mark, so that's a function. We can draw this in a way that's instructive. So a function here, you could consider it to be ordered pairs, x and the function value of x, and in that way of seeing it, you'd find a set of these ordered pairs, which was a subset of the Cartesian products. And if you do that, then you have these 2 situations here that you want to avoid, given those 2 here. So if we have a little function here from x to y, then we have some elements here. Maybe these go to the same elements, maybe there's some other elements here, who knows. But we don't want the case where you have elements here, maybe like that element there, that does not get a function. Like one of you students, if you don't get a mark, that's not great. That's not a great mark-giving function. So we want this not to happen. And we also want the other situation here to also not happen. Or we want f to be unique. So if we have some function, some elements of the codomain here in x, we don't want that you're given 2 marks or more, so to speak. We don't want more than 1 function value. That's not a very well-drawn codomain there, but it is nevertheless what it is. So you don't want this sort of thing to happen, that you get 2 or more marks, so to speak, that this x here gets more than one function value, f of x. So this is also a situation that may not happen if you have a function. So we can visualize functions as subsets of the Cartesian product that don't have this sort of thing occurring. So now to look at this particular triple of examples that could be functions or couldn't. So we see, if we look at the first one, f, that there are some ordered tuples. So a has the function value 2. So student A gets the mark 2, for instance, if we think about that analogy. But a also gets the mark 4. And then we're in that situation there where this could be a, and this could be the marks 2 and 4. So then we have the situation that a gets 2 marks, and we don't want that. So this f is not a function, because a would then have 2 function values, which we're not allowed. Looking at g, well, there aren't a lot of ordered tuples here. In fact, there are none containing a. So a isn't getting a mark, so to speak. A isn't given a function value, so that can't be a function. We've got this situation occurring where we have a isn't given a function value. So this is not a function either. So by psychology, we've had an example of this happening and now an example of that happening. Finally, we must just have that the last one must be a function. Of course, but let's just double check to make sure. So yes, we could draw it up. Let's see. We have a little, let's get a better pen. We have A, B and C, A, B and C, and they are given some marks, like here we have 1, 2, 3, 4 and 5. A is given the mark 5, if we're still thinking about marks, or the function value 5, that's equal to h of A. B gets the mark, or the function value 2, and so does C. So that's perfectly great. So 2 is equal to the function value of B and also the function value of C. So you can see that every one of these elements on the left-hand side in X gets a function value and exactly one function value. So this is a function, and we put a big tick there. Maybe let's put it in green just so that we have something resembling the, yay, that didn't make much difference, but there we go. So this is a function, and yay, we see that function values, they might be the same for different elements, and we'll get to that later where we discuss different types of functions, some of which don't allow that, for instance. And we see that 1, 3 and 4 were potential function values. They were in the codomain, but they're not actually function values. And that brings us to another concept. If you do have a function, then you have the codomain, the domain there, the codomain, but you have one other set that's affiliated to it, that's associated to it, and that's the range or the image. So the range, I'm finding it's hard to find pens that are working greatly at the moment. So let's see. So we've got the so we have the range of H, or also called the image of H. That's supposed to say H. That's equal to the set of function values. So, function values, and here we're talking about the function H. So H of X for all X in the domain. In this particular case, well, what is that? That's equal to 2 and 5. They are the two different function values that we have here. So 2 and 5. And there we go. So we have the domain, the codomain, and the range, or also called the image. They are the three fundamental sets that we're looking at in connection with the functions that we have. So what do all of these sort of functions have to do with the functions that you are generally used to? Like, let's take x squared, the simple, very basic function that we could think of. And if we wanted to plot a little graph of it, we could have x here, f of x, and this nice little parabola there, which is f of x is just basically given by x squared. So that's a function. We know that this is a function. How would you represent it in this sort of language? Well, we could say f goes from the real numbers here on the real axis, and it gets sent to, and then we have to choose our codomain. Now we want our codomain to include the range, so the range was all the function values, but we can make the codomain bigger than the range if we want. It's really up to us and what we need to use it for. So for instance, we could just say that it's all the real numbers. So we don't have to have that all the real numbers are function values, but we just have to have that the codomain, which I've written there, if you might just be able to read it, the domain and codomain, it contains the range, so that's fine. And the function is just given there. We can write it up here again. And then we can represent this function in this sort of way as a subset of this Cartesian product where x and y are, in this case, the real numbers and also the real numbers. So if we write this here, we'd have that the function f can be represented like this, x and the function value, which is x squared, where x is in the part of the real numbers here, and this is a subset of r times r. And that makes great sense, because if you look at the graph here, we're drawing things in the plane, r squared, which is the same as r times r. So we're talking about points in the plane, and that's exactly what this function is. It's a bunch of points in the plane, but it does have the particular property that if you look at any x here, like x there, then there is a unique function value. There is a function value, and there's exactly just one. So f of x is the function value of x there. So that's how this relates to our framework here. Now we also have the range of x, and you can see, well, that's the set of all the function values. So here the range of x, the range of f is all the set of function values, which is just all the set of y's in R, such that y is greater or equal to 0, or you could write that as the interval from 0 to infinity. So that's the range of f. And you see that that's not the same as the codomain that we chose there. But if we did choose the codomain to be exactly the same as the range, for instance 0 to infinity, then that would be another function, technically not the same function as before, but we'd see the same points in the plane. We just defined our codomain to be a different one, which is okay, as long as the codomain includes the range or has the range as a subset, then this is a valid choice of codomain. Here are two particular functions which are quite often useful to have, the floor function and the ceiling function. The floor function rounds down and the ceiling function rounds up. So rounds down, and the ceiling function rounds up. Rounds up. So we can express it in set terminology. If you have a real number x and put it into this floor function, it'll take the biggest integer, the maximal of the integers that are less than or equal to x, and conversely the ceiling function takes the smallest whole number, the integer, that is bigger or equal to x. So if we look at these numbers there, let's find the floor and the ceiling of each of them. And you might want to do this yourself, so pause the video if you like and first do that yourself. I'm sure that you know these functions already, but this is mainly just to remind you. So the floor of this, we have to look at the integer line, the real number line here, and we've got 3, s there, 3, 7 there, and the biggest integer that's smaller than 3, 7 is 3. So we round down to 3. If we round that up, we get 4. Now, if we have a negative number, it doesn't matter. Here we've got some negative minus 3.7. We're thinking in the same way. We're looking at the numbers that are biggest with respect to being smaller than this number. So minus 4 is on the left-hand side of this number there, and it's biggest and yet smaller than biggest among the numbers that are smaller than this number. So this is minus 4, and if we round that up, then we have to go up the scale and we get to minus 3. So you have to be a little careful with those signs. If we have 3 here, we round 3 down, but 3 is an integer already, so we're not actually changing the value of 3. And the same thing if we round up. If we round 3 up to, well, we just get it to self because it's greater or equal to itself, so nothing changes. So whenever we put an integer into these functions, we get the same numbers out of it. And that's also true for the negative numbers here. So here we have -3. You get -3 out of it, whether or not you're rounding up or down. Now, let's also draw these in terms of graphs. What do they look like? Well, the floor function would look like this. So we have our x's there and our function, the floor of x there. So if we have 1, 2 and 3 and so forth, and we have -1. Well, let's look at what happens if we are in 0, 1, 2 and so forth. This was 0, this was -1, sorry for the mess, clean it up, there we go. So if we are in 0, then we get 0, and in fact at every integer we have that the function gives us the same value out, so we've got those function values there. If we're a tiny bit to the left of an integer, we're rounding down, so we snap to the integer that's below it. In this case, if we're between 0 and 1, we're rounding down to 0, so the function value, if you can see it, is there. And then we draw a little round bubble to say that when we get to 1, there's a discontinuity, there's a skip or a jump up to this value. And then after 1, we round down to 1, except then we get to 2, and we keep going at 2, and so forth and so on. So this is what the graph would look like if you have these values here. And this would be a round thing there, and a round thing there, and so forth. Now we might as well use the same diagram to show this the ceiling function. Here we're rounding up. So here, if you can see this different color, if this is in this, let's use pink. That's a bit more visible here. And so pink, and then we'd have, okay, 0, we've again got the function values not changing if we're talking about integers. But if we have something a little bit bigger than 0, then we round up to 1. So there's a continuity there, and we have this picture there. So now we're rounding up. So here we go, and so forth and so on. Okay, so these are the floor and ceiling functions. We haven't really talked much about the domains and codomains for these so far, but we could define each of these, for instance this function there, to be from all of the real numbers, which it is, to, well, something containing the integers, because we only get integer values. So we could define it like this, or we could say, well, the codomain is the reals because they contain the integers there, and so forth. And the same would be true for the ceiling function. Now, what's the range of these functions there? And now I'm running out of space, but the range of each of these functions, like for instance the ceiling, is just, well, what is it? Well, it's all the integers, because they are all the function values that we get. Any integer is a function value of itself, so the range is exactly just the whole set of integers. Yeah. So here we have an exercise, and you might want to stop the video and complete it yourself. What we have to do here is to figure out which of these three things that we've written up here might be functions, and also if they are a function, we have to find what the range of these functions are. So we have to check that these things that we've written up satisfy what we've got written over there. In particular, we need that every element of the domain, so in this case the reals, that each of those elements there have a function value, so that f of x exists, and f of x will in that case be unique because we've written it up in a unique way over there. So let's check that. Well, is the first one a function? Well, so it's x squared. That sounds like a function, but what happens if we plug a negative number into it? Now, you could define that in terms of complex numbers, But we've also been told here that we want our function values to lie within the reals. So we can't do that. If we plug -1 into that function there, we get the square root of -1, which is not a real number. So this can't be a function. We can't find a function value for the negative numbers here. What about g then? Well, now we're sending the real numbers into this function 1 over x. That seems like a perfectly nice function too, but we do have one little problem. All of the reals can be stuffed into that function and give a well-defined result, except for 0. 1 over 0 is not defined. We could define it, but it's not going to be a real. Not going to be a real number, and the codomain has been chosen to be real numbers, and all the function values have to lie within that set. So that is not a function. Now, if we did modify it a little bit, if we had g2, so modify it a little bit to be equal to the function on the reals minus the 0, so we're carefully removing that exception, and we let the codomain be the same, that's fine. And now we define g2 of x to be equal to 1 over x. Well, now that actually is a function because we've modified it just a little bit. We don't require anymore that we have to try to put 0 into the function. So by changing the domain, we have turned what wasn't a function into a function. So the choice of domain and codomain are rather important here, but they're also possibly somewhat arbitrary. Like here we chose this, here we chose that. We could have chosen maybe the positive integers or something. That would be valid as well. Okay, so the last example here with h, we have had no, so it's about time that we have a yes. So let's guess that this is a yes, and let's double check it though. H sends real numbers into real numbers. Okay, so the codomain is real, or the real numbers there. H is just this parabola, okay, just a parabolic expression, a second degree polynomial in x, and yeah, sure, there's nothing wrong with that. If we plug any real number into this expression, we will get a real number out of it. The function values h of x for each x are defined, so yes, this is indeed a function. And the range of x, the range of h, that's all the function values there. And I might just explain how to find them. This you can sort of recognize a little bit as x minus 1 squared minus 2, and that's equal to, that's greater or equal to minus 2, and in fact it's equal to minus 2 when we plug 1 into it. And in fact you can see that it's a continuous function, so this grows to infinity, starts at minus 2, so in fact the range of this function here is indeed all the numbers from minus 2 up to infinity. And now I've sort of squeezed things a little bit, but I hope you can still read it. So they were some more exercises about what is a function and what is not.